Hi everyone. I guess I was already introduced, but still, I'm Francesco. I'm a researcher at the EF, mostly focused on the consensus layer. And I'm here today to talk to you about the approach that we take into scaling Ethereum, which is a iterative incremental one. But first, let's start with a recap of the rollup-centric roadmap so far and all of the steps we've already taken, which are many. At the beginning was just Ethereum, this standalone blockchain executing all transactions, no rollups. Then we've moved maybe around 2020 to having first rollups coming live, basically other blockchains posting their transactions on Ethereum as call data in particular, and Ethereum not executing any of this, but only verifying the correctness through optimistic proofs through fraud proofs or validity proofs. And finally this year, like a big milestone, we've moved on to what we could call like the first scaling era of rollups through EIP 4844. Blobs have been live, and you can already see from this picture things look a bit different. Now transactions go in this, these sidecars, these blobs that exist outside of blocks that the EVM cannot access. And yeah, just for making sure that no one is upset, here's just substituting with other logos so that everyone can find their favorite rollup. But what have we actually achieved with blobs? Like why was this a big milestone? Why have fees gone down and so on? Why are we scaled in some way? And there's a few reasons. The main reason is that blobs essentially have an independent fee market that it's completely separate from the execution fee market. So this is probably one of the biggest components of the way that blobs already scale something. And then the other component is that they're only stored and served for 18 days as opposed to for all of eternity. And so this allows us to be much more comfortable with higher blob throughput. And another thing that is not in immediate output to scaling, but that is very important in this iterative roadmap that I'm trying to tell you about, is that we've kind of laid the cryptographic groundwork and foundations for future upgrades. So in particular, the KZG ceremony and all of this cryptography being introduced to Ethereum. And yeah, now the question is what's missing? Why was this upgrade not enough? And we need to keep moving forward. So still the issue is there's no sharding. All blobs are being downloaded by everyone. A block proposal process looks the way you see here. There's a block proposer with a block and some associated blobs, and it broadcasts everything to the network through in these what we call blob subnets. So these like kind of sub-networks that are specifically for blobs. Well, we call them subnets, but they're not actually subnets. Everyone is actually participating in them. They're what we call global gossip topics, just like the topic that we use for beacon blocks. So the whole network is downloading both the block and blobs. So we haven't still really moved from the fundamental bottleneck of bandwidth, which you might have seen that is really coming up more and more as the scarcest resource that we have. And how do we solve this? We moved to data availability sampling, or we introduced data availability sampling to the protocol, which is essentially the next big goal for scaling Ethereum or the DA layer of Ethereum and the rollups that they use it. So first, a small introduction to what is data availability sampling. It's something that in abstract has been talked about for many years, so probably many of you are familiar with it, but still, at a basic level, essentially, we take what's on the left, which we could think about it as just any kind of data, but let's think about it as a blob, this blue part, and divide it in a bunch of chunks. Then we erasure code it, so we essentially introduce some redundancy to it in such a way that it becomes reconstructible as soon as any 50% of this data is available. And so this redundancy is the orange part, rather than needing the whole 100% of it to be available. And what this allows us to do is essentially to be able to check availability just by checking that any 50% is available, which is a much easier problem. And yeah, so ultimately what do we want to do with this is that we would like users, full nodes and possibly validators as well, to only be downloading a few chunks of data instead of the whole data, which is what's happening right now, to verify that the data is available. Now, what does it, so that's, abstractly, we could talk about this, but what would it look like in practice in Ethereum? And what is it going to look like in practice, maybe in the next fork or whenever this comes to the network? And yeah, so, we have many blobs, we don't just have one blob. So the way we do sampling and, the easiest way we can think about doing sampling is to just essentially stack these blobs together, create this sort of rectangle, this matrix. and then extend all blobs horizontally, the same way I showed you before, independently of each other, but then doing sampling on this whole matrix as opposed to on each blob individually. Now, this actually, in some sense, is the same thing. Like, you can look at this smaller image. That's what it looks like to do sampling on each blob separately. So we choose for each blob some indices, whereas what's on the left is doing sampling on each blob in a coupled way where all of the indices are the same. But why do we call this one-dimensional DAS is because anyway we're doing sampling kind of horizontally only. Maybe one way to see it is forget about the distinction between each blob and just think about the matrix. We can think about the matrix as this kind of fat blob, as like a big line that actually looks very much like the original blob. So it's essentially it really is the same picture. We're just doing sampling on this bigger object, but the underlying what we're trying to do with sampling there does not change in any way. And yeah, so once we've established, okay, maybe we want to do this one-dimensional sampling, it's a simple, like, intuitive way to extend sampling from single blobs to the whole set of blobs that we have in accompanying a block. How do we actually do this? How do we actually put this into the protocol? What do we do with it? And it's kind of a helpful mental model to generally think of incorporating DS into the protocol in 3 phases, or thinking about how to do each phase individually. So the first phase is distribution, which is essentially there's a block producer, it wants to send a block and accompanying data, so there's some kind of extended matrix of blobs to the network, and it first of all has to get this data spread out, essentially. So it somehow has to push this data to the network in some way, and so we have to figure out what is this way. Then the next phase is sampling. So once the data exists somewhere in the network, how do people actually do sampling? How do they get the specific chunks that they want? And then also another question in sampling is, what do they do with it? So how does it actually impact their behavior? And this kind of has 2 components. One is it impacts your behavior in the for choice if you're a tester. And also it impacts your behavior in transaction confirmation. Like, how do you decide that a certain transaction that I want confirmation for is actually confirmed if I'm not downloading the whole data? And we can use sampling in different ways in these kind of decisions. And then the last phase is reconstruction, which is quite important, and it is sure, the data might be 50% available, but eventually we actually want to be 100% available. We want the whole network to agree that it is available, and we want to be able to, like, everyone to retrieve all parts of the data that we care about. So, for example, look at the image above. It's this kind of red, like, corrupted network where some columns are missing, these black columns, but actually most of the data is there, more than 50%. So in principle, it is reconstructible, and somehow we want to eventually this to happen in practice. So we want to go from the red to this kind of blue, like, healthy network where everything is back in the right place. And yeah, now let's kind of think about what do these phases look like in the data availability sampling, the concrete data availability sampling protocol that will most likely ship in Fusaka, which is the fork after the next one, which is Spectra. And there's a simplification already in Fusaka, and in this particular way of doing data availability sampling, in that distribution and sampling are essentially the same. They're done at the same time, in the same phase, essentially. So if you remember the picture that we had before, we had a block proposer sending a block and blobs through certain subnets. Now we essentially substituted the blob subnets with these, which you can think of as horizontal subnets, with these vertical subnets where columns are sent. So we've kind of moved from sending blobs to sending columns around, which are the the units that we now care about, the samples that people are supposed to eventually be trying to get. But we're still using the same kind of networking infrastructure underlying to do this. So the same way that now, literally today in production, we're sending blobs, we will be sending columns. But the difference from before is that you don't participate in all of the column subnets. Like, you as a random node, as a someone that's running one validator, or as a full node, you will only participate in a subset of these. So essentially, your participation in these networks already decides which kind of sampling, like which essentially samples you're getting. So you choose which network to participate in, or which gossip topics to participate in, based on the sampling that you want to do. And so here, really, we've moved beyond the 484 limitation that everyone is downloading everything. And then, yeah, reconstruction. Like, at this point, the assumption that will exist in order for reconstruction to to happen is a kind of one-of-n honesty assumption that there should be at least one node in the network that is willing to download all of the data and then do reconstruction if necessary. So essentially, we go again from this like red corrupted network. There's this one node, at least one, but of course we would hope there's more than one, that downloads everything, downloads all of the things that are not black, that are actually available, does locally reconstruction, recomputes everything, and then pushes all of the kind of healed data, all the missing data to the network. And just to call it out, this is not actually necessary. We don't need this assumption. It's just something that seems like a reasonable thing to start from, and it can simplify certain things. But it's even very possible that the spec might change in this respect, and we might move to something that actually supports distributed reconstruction, which is very much possible. And yeah, just to kind of go more in depth on the distribution slash sampling part, what does it look like in practice is that the whole matrix is divided in 128 columns specifically, and you only need to download 8 of them. And so you can think of this as essentially being 1/16 of the extended data. So once you look at the matrix that includes both the blue and the orange part is 1/16 of the data. That's kind of this minimum that you need to download, or 1/8 of the original data. So in some sense, the scaling factor that we would get with these parameters would be 8x compared to 4844. Now, what does this mean in practice? Essentially, yeah, I mean, there's this kind of 8x scaling factor. In the next fork Pectra, the idea is that we would most likely have a target of 4 and a max of 6, or maybe even more blobs. Currently, it's 3 and 6. And so, you know, if you apply just naively this 8x factor, you would get to 3248. So a 4 basically megabytes per slot target, which corresponds to roughly 1,800 ERC transfers per second, and that's uncompressed. And yeah, it's also, I guess, another way to think about it in terms of a milestone would be that this is 4x away from the original goal of, in some sense, the midterm scaling roadmap of Ethereum, which was 128 blobs. So we're actually hopefully getting close, or we will once this upgrade is actually on mainnet. And yeah, but still, it's some 4x away or however much away. Where do we go from there? Like, how do we fill still this remaining kind of gap between where we are and where we want to get? And there's some immediate possible things we could do. I mean, there's really many things. The design space is quite open, but in terms of very concrete kind of, again, in the spirit of this like just iteration on what we have, some concrete next steps are that we could, for example, just make samples thinner, so we could have more of these subnets or gossip topics. Instead of 128 columns, you could have 256 or however many, and thinner samples means less bandwidth. Another thing we could do that's a bit more advanced, let's say, and more like an interesting step, I would say, in the design space, is we could try to reduce the gossip overhead that comes with all of these things being propagated in the network. Because right now, it all happens very much in the critical path of a proposer tries to push a block and blobs through a network, and it's really time critical. There's only a few seconds. Everyone's supposed to get it in these few seconds. So the timelines are very much compressed, and because of this, there's a lot of redundancy. There's a lot of people downloading and uploading things multiple times instead of just once. And so yeah, maybe there's ways to relax these sampling timelines and do a bit more of, like, for example, pulling instead of pushing, and essentially try to reduce this redundancy. And I'm gonna call out like one research direction that's come up from multiple people lately, which I think is quite interesting, which we might call mempool sampling. So going back to the picture that we had before with distribution, sampling, and reconstruction, actually we've kind of ignored a pretty important part of the whole kind of pipeline of getting a blob from the transaction sender all the way to being confirmed by the network in a safe way. And yeah, it is really the sending part, the part where you actually make a transaction, attach a blob to it, and you send it to the mempool, as most of the time would be the case. And yeah, this part is actually quite important, and we can exploit it. So this happens much before, or at least a few seconds before normally, then a blob actually ending up attached to a block and kind of been sent in this kind of critical path that I mentioned before. So what we could think of is to essentially exploit this time in which blobs are kind of just floating around in the EL mempool to already start doing sampling. So another way that this has been called is vertical mempool sharding, because you can think of it as, eventually eventually we probably do want to shard the EL mempool. We don't want everyone to be downloading all the blobs, neither on the CL nor on the EL mempool. But specifically, we could do this sharding in this vertical way where the things that you download are across blobs, as opposed to saying you only download some of the blobs, you download all of the blob transactions, but only some chunks from each blob. And now again, I didn't repeat the meme, but again, it's the same picture. It's the same picture you've seen before with doing sampling on columns, except in this case, you're doing it on each blob, and then these blobs might be put into a block by someone, and you could kind of go back to the second picture, essentially. But to kind of clarify it more, let's look at the whole kind of pipeline of what this could look like in practice. So there's a mempool on the EL. There is people that are making blob transactions and sending them to it. The blob transaction now would already come encoded. They would come with this like erasure coding already done by the transaction senders. So the EL mempool would already have this like orange part, essentially. And people would be normally just sampling from there. Somehow the block proposer would get these. For example, it could try to really hard to just download everything at the time when it needs to make a block. This is actually very much not prohibitive in terms of bandwidth. So it's much easier to just download blobs the one time that you need, as opposed to be like constantly participating in this like full mempool. Yeah, the block proposer would basically just send out actually the block, not even the blobs. It would not try to push the blobs to the network at all, which is costly. It requires a lot of upload bandwidth. It requires you to upload these blobs to or columns to many of your peers. So it's much more prohibitive to do. So you would just be sending out the block, and some other node would be receiving the block, know which blobs it needs to care about, and it would already have done sampling on the blobs in the mempool. So the sampling would have kind of already happened in advance, essentially. And at that point, the other node, which only has these few columns that it kind of reconstructs from putting together the sampling that it has done, it could already conclude like, sure, this block is fine, these blobs are available. And for example, in the case of in a tester, it could vote for this block. And yeah, let's go back then to the original question: how much could we scale the Ethereum data layer if we, for example, were to do something like this? So we have like a few factors that make it easier to do so. Like one is that now sampling would happen on like a slot timeline instead of on this block proposal timeline, which is much more compressed. So it would be 12 seconds instead of 4 seconds. So there's kind of a 3x factor there on roughly speaking on average. And yeah, so that's one thing. Like sampling timelines are generally relaxed. You can do sampling in a much less aggressive way as well. We don't need to be accepting so much of redundancy and of waste. We can try to be a bit more like conservative. For example, really trying to only get one copy instead of many copies. And there's no duplicate work between EL and CL. We only have blobs existing essentially in one place, as opposed to existing first in the EL mempool and then being again like broadcast a second time on the CL. And another thing is that it might not have been obvious from the previous picture is that it kind of supports local block building by default. As I said, you would not really need a high upload bandwidth or to be doing any expensive computation in order to propose a block with a lot of blobs. Because the hard part, which is like pushing out these blobs to the network, actually would have already happened in the EL mempool, and it's not something that you would need to take responsibility for. It would be more of like a network-wide responsibility. So it's in some sense this kind of distributed block building idea that has been in some sense the holy grail of this whole section of research. And yeah, the idea there is that, okay, we were 4x away. We have now like a few things that seem like to be pushing us in the opposite direction. Hopefully we can actually then scale to 128 blobs. Of course, we have to see this in practice, but it in principle seems at least very plausible that we could be able to do this. And just to call it out, that would be like around 7,000 uncompressed like ERC20 transactions. Then you can choose your favorite transaction type and favorite compression algorithm and see how much that actually corresponds. And there's a lot that I didn't talk about because it's only 20 minutes, so I just put some random pictures from my Draw.io with some other things that might have been interesting in a different talk that went into a different direction. That's kind of 2D sampling. You might have seen this somewhere. That's some kind of version of peer sampling. That's something that's trying to tell you that if you're talking about full nodes, you actually don't need them to be doing sampling very fast. You could do sampling on like a finality timeline, which is very slow. So you can kind of play with this a lot, and you can use like a black box that's much different. You could use very obscure sampling constructions for this. But yeah, all of these things, didn't have time to talk about them, but the message there is that there are a lot of research ideas that are very interesting in this space, and we should keep exploring them to eventually get to the best ones. But thankfully, this does not come in the trade-off on not being able to scale today, because we can already scale with what we have and with like a simple iterative approach, and in the meantime, keep researching what's to come next, essentially. And yeah, that's all. Thank you very much. These are some resources, like a bunch of list of blog posts that might be interesting if you want to learn more. And yeah, small plug, like we're very much this is a very important project for Ethereum. There's great, interesting things to work on. So if you are interested in working on a P2P network, we are hiring, and yeah, this is a really great opportunity to work on something impactful, like extremely impactful for Ethereum. Thank you.
Thank you, thank you. We have a little bit of time for a few questions. So we are going to kick it off with, how urgent do you think is the demand for more blob space?
I think it's pretty urgent. I mean, they're saturated essentially as we speak, and I think demand from rollups will only increase. So yeah, I think it's very much like a top priority for us, and I think it should be for the Ethereum ecosystem in general.
Thank you. Is it a CPU-intensive task to reconstruct blobs? Each node will do reconstruction at the receiving block for checking KZG commitment, or is it add significant time for importing block?
So you don't need to be doing reconstruction in the normal case. You only need to be doing reconstruction when things go wrong. It's not extremely CPU intensive. I mean, if you had to do reconstruction of the whole matrix, that something that you might need like a few cores to do efficiently. And also this is one of the reasons why doing it in a more distributed way, where you only can reconstruct you only need to reconstruct one blob at a time to actually help the network, would be nice. And this is something that, yeah, we could even consider doing in like a first rollout. But yeah, generally speaking, it's not something that's incredibly CPU intensive.
How far can we take this before it breaks down?
It's a hard question to answer, because I think you have to specify what exactly breaks down. I think there's, yeah, I would say right now, one of the main bottlenecks, like the thing that you could say breaks down first, could be local block building, depending on how things are implemented. Like, you could do this in a way where it becomes really difficult to do local block building at high blob count, which does not mean that you could not do it, but it might be difficult to do at high blob count. But I think a lot of what's hard about doing these things is doing it in a way that does not compromise on a lot of these like nice properties that we have. And so, yeah, I think we can actually push this if we do this carefully and like mindfully, and we try to take the right approaches instead of shortcuts. I think we can do this in a way that does not break down in any of the things that we care about.
Can DAS decrease bandwidth requirements on some actors in the network? Yes.
Decrease. Okay.
Mm-hmm. Yes, decrease.
If
yes, then on which?
Right. Yeah, I mean, for example, I mean, it really depends on a combination of DS and how much scaling. Like, for example, if we were to do, what's now PeerDAS, like the PeerDAS, in the PeerDAS spec today, and we did not increase the blob count by a certain amount, by, more than a certain amount, then it would decrease bandwidth requirement for essentially full nodes and validators with a few nodes with a few validators. Kind of the idea is that if you have a lot of validators, you would still be downloading most of, like, and when I say a lot, it means like, hundreds, like you're really putting like tens of millions of dollars on your node, then you'd be downloading a lot of the data. If you're someone that is just a full node or downloading a few, or running a few validators, you would be downloading like only these like few samples, and that overall would, yeah, it should decrease your bandwidth requirement unless we scale to the maximum possible, essentially.
And next question, does this mean that there's a minimum peer threshold in order to reconstruct blobs, and what is this threshold?
Minimum peer threshold. Yeah, I guess I'm not entirely sure in what exactly the question means. A minimum peer threshold in order to be able to be connected to all of the subnets, in order to get all of the data. Or, yeah, it really depends, because, for example, you could be connected to like a single other node that has a lot of the data, or like a few other nodes that have a lot of the data, then you could need just a few peers. But if everyone around you is only doing the minimum amount of work, you will need more peers. Still, yeah, I think the network would be very heterogeneous in this sense. So you would have some peers that only do like a few, like the minimum amount, some peers that do anywhere in between the minimum and the maximum. So it's kind of hard to say. It really depends on like what this heterogeneity in the network ends up in practice actually looking like.
And I think we're going to do one more quickly. Who checks the erasure and coding from the TX sender?
You just check proofs. Like there's this KZG proofs that just tell you that it was done correctly, essentially. And it's actually very fast to check.
Awesome. That is all the time we have. Let's give up a huge round of applause for Francesco. Thank you so